Now, this much introduction about basics of functions of several variables would be sufficient for now. Let us now concentrate on the properties of functions of several variables, which are interesting from the point of view of calculus, that is, limits, continuity, derivatives, and of course, related geometry. Now, in some cases, this will be almost word by word the same as the case of one variable functions, but sometimes there will be very basic differences. Okay. So we discuss now limit of an f from R2 into R. Okay. As I already mentioned, we will be considering functions from R2 into R, basically. But in many cases, we will comment that it's also true if f is defined not only in R2, but in R3 as well, or higher dimensions. But the range will be R. So let us recall that for a function of one variable, okay, limit x going to x0, f of x, is L, means for every epsilon, there is a delta such that if the distance between x and x0 is less than delta, then the distance between f of x and L is less than epsilon. This was our standard definition. Now, for our case, if f is from R2 into R, okay, limit, of course, now we have to take our variables from the domain, which is R2. So I will show it with P going to P0. F of P is L, okay, means, okay, by direct imitation, for all epsilon, there is a delta positive such that if P minus P0 is less than delta, then f of P minus L is less than epsilon. Now here, let us look at this definition and see what changed. Okay. Because f of x is a real number, absolute value measures the distance perfectly well. Well, here we had real numbers, we used absolute value. But we want to measure distance, and here we have vectors. So we have to use the length of the vector. If the length of the difference is small, it means the vector p is near the vector p0. So the only difference comes here. Okay. Since a distance okay, we write p minus p0. Otherwise, it's the same definition. So, not much changed in here. Okay. Now, because this limit definition for a function of two variables, okay, is, word by word, the same as in the case of one variable. Okay. We expect that all the properties of the limit connected to the original definition should also be correct in this case. They are. Okay. The limit properties are exactly similar. One can prove these as we did for a function of one variable, step by step. What are these properties? Okay, so let limit p approaching p0, f of p be f, limit p approaching p0, g of p be g. Okay, these are functions of two variables now. Then, okay, we have limit p going to p0, a multiple of f of p plus g of p. I'm combining the properties here as a first property. This is cf plus g. So you can calculate the limits one by one, add them, multiply them by a scalar. This is just the same as in the previous case. This is called the linearity. Okay. 2, we can multiply limits, namely limit p going to p0, okay, f of p, g of p will be fg. Okay. Same thing as before. The limit p going to p0, f of p divided by g of p. Now these are real numbers, so I can perform standard operations, binary operations on them. This would be f over g. Of course, g must be non-zero, otherwise the whole process would fail. And squeezing theorem holds. Is also valid. Okay, to these I can add some more properties. Well, for instance, let me write it. If if limit f of p, p going to p0, in absolute value is 0. Well, let me not say if. Okay, this is 0 if and only if the limit p going to p0, f of p is 0. So if the limit is 0, whether you put absolute value or not, nothing changes because of the same inequalities we used as in the case of one variable. We will be using this over and over again. Note that these properties would not maybe hold or even make sense if the range was not R. For example, if it were a function from R2 into R2, okay, as in 3, you cannot divide vectors. So there would be a problem. But in this case, everything works fine. So we have the same nice properties. All right. Let us work this out because there will be slight modifications. Okay, show that, okay, using definition. Okay. Limit, I can use anything here, but I don't want to complicate matters, so this should be easy. Okay, so say x minus y plus 2, when x goes to 1 is 2. Clearly, this is a function of when xy goes to, say, 1, 1. Okay. So this is my p, this is my p0, and this is my f of p, or xy. Okay. So how does the definition go? Given an epsilon, okay, we find a delta, Okay, we will find it in a minute, such that if this is true, okay, then x minus y plus 2, that's the function, f of p, minus L, well, here L is even given as 2, okay, is less than epsilon. So this must be satisfied. Okay. Now what do we have here? Well, clearly this tells us that, okay, to obtain this, we don't know this yet, so let us continue from here. It is x minus y. Okay. X goes to 1, y goes to 1, so I can write this as x minus 1 plus, okay, or rather minus y minus 1. Okay. I subtracted and added plus 1. Triangle inequality says that this is less than this sum. Now, x goes to 1 and y goes to 1, so both of them should go to 0. They both will be small. Okay, do we get this from this condition? Okay. To see this, let us check what this means. Now, since xy minus 1, 1 means exactly x minus 1 squared, y minus 1 squared under the root, okay? Clearly this is greater than x minus 1 in absolute value. Because take squares of both sides, everything positive, you can do it. Here you have an extra positive term. But also, it's bigger than y minus 1. And this was less than delta. Which means that if this is less than delta, 1 by 1, these are less than delta. So, okay, so we get that f of xy minus 2, which we calculated there. I'm not repeating that. This is less than 2 delta. What do we want? We want this to be less than epsilon. So here, we have to choose delta, for example. Epsilon over 2, it works. So we go up. Okay, let me put an arrow here. Choose it as epsilon over 2. So how does it read? Given epsilon, we choose a delta, which is epsilon over 2. And if this is true, which means both of them are less than epsilon over 2, and we get epsilon, so we are finished. Indeed, the limit is 2. So what was the difference? Well, because we have a vector distance less than delta, it gives us both x minus x0 and y minus y0 smaller than delta, and we can use it. So this is using the definition. Okay. As a second example, let us show that limit xy goes to 0, 0, x squared y over x squared plus y squared is 0. Now we can use the definition. Exactly. Actually, we will be doing the same calculations anyway, But let us use squeezing theorem. Okay, what does that say? Okay, we look at this term, x squared y over x squared plus y squared. Of course, xy is not 0, 0, which means the bottom is not 0. So we can do it. This is exactly x squared over x squared plus y squared times absolute y. Now, this term is always less than or equal to 1. So this is less than or equal to absolute y. The absolute value cannot be negative. And this one goes to 0, obviously. This one goes to 0 when y goes to 0, x goes to 0, and y goes to 0. So we know this. Now, by squeezing theorem, this also goes to 0. Now, so by property 5, without absolute value, we also have limit p going to 0, 0, f of xy is 0. So we can use either the squeezing theorem or the definition to show a certain limit exists at this point so far. Okay. Now, it is also interesting to discuss how we can show that a certain limit does not exist. Okay. So, let me say this as a remark. Okay. If f is a function from reals into reals, then showing that limit f of x does not exist, okay, can be done by showing that limit x going to x0 from the right side is not the same as x going to x0 from the left side, or just one of them does not exist. So, in the case of one variable, okay, if the right and left limits are not both exist, but they don't, they are not equal, then we could say there's no limit. Fine, we can calculate them and we are done. Okay. Or if one of them, the right or the left limit, does not exist, then we could directly say there's no limit. Because if there were a limit, both would exist and they would be equal. Okay. Why are the right and the left limits exist? Why are they important? Is there a third way? No. Because, okay, in R, okay, if you look at x0, your x can approach, so x can go to x0 only, okay, from two sides. There is no third side. So if you guarantee both cases, okay, as we did here, if they are equal, fine. You have a limit, otherwise you don't have a limit. But for f from R2 into R, okay, There are many ways. P can go to P0. Okay. Let us look at a picture. It will be understood better. Say this is my P0. Somewhere here, I have a surface, and, okay, well, let me put it somewhere here. That would be better. Okay. Say this is the level. It need not be full. This is the level L. Now, we want this L to be the limit. Okay, P will approach P0. Well, how can it approach P0? It can approach okay, from a straight line like this, or from here, or from here. It need not be a straight line. It can even approach on a parabola. So, sorry, there are many ways P can approach P0. At the top, what does this mean? At the top, it means that P approaches like this, because at the top, the straight line is not a straight line anymore, so it's a curve. Well, this can approach this way, or this one can approach this way, and there are lots of ways we get. So the level L should be the same for all approaches. Okay. So then, okay, if P approaches P0 on any curve, okay, of course, which passes through P0, and okay, limit f of P, P goes to P0, but on a fixed curve, okay, on okay, some fixed curve, is L, okay, but these fixed curves are any curves, so for all such curves, we get L, then the limit exists. In other words, to show the limit by curves in multivariables, we have to consider all possible infinitely many curves. Well, this is quite insane, not practical at all in many cases. Whereas here, just looking at two curves was enough, and it was easy. But to show that limit does not exist, now the two-variable case has an advantage. However, to show that limit f of P, P going to P0 does not exist, okay, again, concentrate on this remark. To exist, all curves should give the same limit. So for this not to exist, it's enough to find two of them, which give you different values. Okay. It suffices to find, okay, just two curves giving different limit values. Okay, this remark will be clear from the examples in a minute. Or some curve giving no limit. So we can choose two curves from among infinitely many ones. Now, this is an advantage. We didn't have this in one variable case. But their calculations were relatively easier, of course. Now, let us see this in some examples. Okay, let us consider a limit, say xy, going to, okay, let me give a simpler one first. Sorry. Well. Say 0, 0. Say xy over x squared plus y squared. Now, the suggestion is that, of course, that this limit does not exist. So we want to show it. For this end, we try some curves. By the way, why do we try curves? Because we did in one variable, but that's not good enough. Okay? We try it because if we restrict p approaching p0 on a curve, okay, we reduce the limit to one variable, where we are quite experienced. So let us try. Okay? Now this is p0. Say the curve is this. The y-axis. Okay, so we look at limit xy goes to 0, 0 on y-axis. Now, what does this mean? Well, we are on the y-axis. So, x is 0. Okay, and y, okay, x goes to 0, but x is 0. So, this is the same as 0y going to 0, 0, or just y goes to 0, of 0 divided by 0 plus y squared, because x is 0. Okay, x is not going to 0. It is equal to 0. So it's not a limit. But, of course, y goes to 0, so y is not 0, which means that the ratio is 0, so it's the limit of 0, which happens to be 0. Now, what does this tell us? This only tells us that on one curve, p is here, approaches p0 on a certain curve. Okay. If there were a limit, all curves should give the same limit value. So if there is a limit, it should be 0. But this doesn't say there is a limit. There may be no limit. Okay. Let us check something else. Say we check this time, okay, a straight line, which is y equal to x. This is p0. And say p approaches to p0 on this line. Call this gamma 1 curve. It's a curve, of course. So we check the limit, xy going to 0, 0. Okay. But xy is on gamma. Now again, what does this mean? This means, of course, that y is equal to x. So this is the limit, okay? Because y is equal to x, xx going to 0, 0, okay? X squared over x squared plus x squared. X is equal to y. And x goes to 0. Okay. Okay. X goes to 0, 0 means, of course, x goes to 0. Well, x is not 0, so we can simplify. This is the limit, x going to 0 of 1/2, which is equal to 1/2. Now, clearly, this is not 0, so limit xy going to 0, 0, xy over x squared plus y squared does not exist. Okay. Now, so far, what we did is we checked, okay, a curve which gave us a limit. Fine. We checked another curve, a straight line for simplicity, and we obtained this. We could have done this a little differently. Okay. We could economize. Namely, okay, check, okay, by checking all lines at the same time. Well, it is not all, of course, because I will be working with the slope, so except the y-axis, maybe. Okay. What does that mean? What is a line? Okay. An arbitrary straight line. It must pass through P0. Okay. Now, an arbitrary line through 0, 0, that is P0, is y equal to mx clearly. At 0, it will be 0, and it will have some slope. I said except y-axis, so for y-axis, this doesn't hold, clearly. So, okay, limit f xy, xy going to 0, 0, but y is mx. So I'm considering infinitely many lines in one step. This means that limit, okay, y is mx, so x times mx, x squared plus m squared x squared, okay, and x mx goes to 0, 0. Now, x goes to 0, and m times x goes to 0. They say the same thing, so it's the same as x going to 0. If this goes to 0, 0, x goes to 0. If x goes to 0, this is true. So this is n x squared over 1 plus m squared x squared. X is not 0, so this is m over 1 plus m squared. Now, what does this tell us? It tells us the following. If we change the line, the limit value will change. That is, okay, we don't get the same limit all the time. So this says there's no limit. Okay, again, this means, okay, on different lines, okay, limit value is different. So there are at least two of them which give different values. So, okay, the limit p going to p0, not on a curve, in general, f of p does not exist. So this looks at all lines at the same time, so it's a very economical way of looking at the picture. Okay. As a different example, which will say that even this will not work in some cases. So checking all lines, that's infinitely many curves at the same time, is not sufficient because, okay, this is a small infinity compared with all possible curves infinity. There are other curves which we did not check. An example for that would be the following. Limit xy goes to 1, 1 of x minus 1, okay, y minus 1 over x minus 1 squared, y minus 1 to the fourth. S squared here. Okay. So clearly, this is again a problematic case because the denominator becomes 0. We have problems. Again, in multivariable case, we don't have L'Hopital's rule. So don't try such things. We don't have such a shortcut. What can we do? Well, as we checked, okay, let us check the case of an arbitrary line. Okay. An arbitrary line through the point 1, 1, of course, means that only the slope can change because the point is fixed. So it means that y minus 1 will be m x minus 1. Passes through 1, 1, and slope is m. Okay. So, okay, let us look at the limit when xy goes to 1, 1, and on L. L is arbitrary, however, so let me just say f of p. This is the limit. Okay. xy goes to 1, 1. Well, y is mx minus 1 plus 1. So it is x, and y is mx minus 1 plus 1, going to 1, 1. This is y, because we are on L. Okay. Now, up there, because of this equality, we can simplify this. It would be x minus 1, okay, times m squared x minus 1 squared divided by x minus 1 squared plus m to the fourth x minus 1 to the fourth. Now, if x goes to 1, of course, whatever m is, y goes to 1. Okay? So, or y goes to 1 means x goes to 1. So I can write this very simply as limit x goes to 1, okay, m squared x minus 1 cubed over x minus 1 squared 1 plus m to the fourth x minus 1 squared. Okay, manipulating a little bit, which of course says that these cancel. Now, if m is not 0, or 0, it doesn't make any difference. When x goes to 1, this goes to 0. Now, this does not say there is no limit, because there is no dependence on m. For all straight lines, the limit is 0. Okay. But it also does not say there is a limit. Namely, okay, this does not say limit p going to p0, f of p is 0, because we did not check all curves. But just lines. There are curves which are not lines. Maybe some of them will give a different value than 0. Maybe our choice of lines was not a good one. Well, we will see that indeed this is the case. Now, since lines did not give us very nice things, let us check something like a parabola. What kind of a parabola? A parabola which passes through 1, 1. Okay. What is the idea here, by the way? The idea is that when we look at the function directly, okay, if we want to get something other than 0, to get a conclusion that there's no limit, we need that. Something different from 0. To get something different from 0, clearly the degrees at the top and the bottom should match. Only then we get something different from 0. To make the powers at the top and at the bottom equal, clearly we should take x minus 1 to be y minus 1 squared. So, let us try x minus 1 be y minus 1 squared. Well, this is a parabola. Maybe a not very easy looking parabola, but it's a parabola. A shifted parabola in both cases. Actually, it is the following parabola. Something like this. Okay? Now, this parabola certainly passes through 1, 1, so we can try it. Namely, the limit xy going to 1, 1. On the parabola, x minus 1 is y minus 1 squared. Okay? We check f of b. Now this is the limit, okay? X goes to 1, and y is the square root of x minus 1. Well, x is bigger than 1 anyway. Okay. Plus 1. That's my y. Or negative root, it doesn't matter at all. And it goes to 1, 1. And in the equation, I have, in the expression, I have x minus 1, which is y minus 1 squared, times another one, and that was the idea, y minus 1 to the 4th plus y minus 1 to the 4th. Well, the powers are matching. That was our goal. And let's look at this limit. X goes to 1, the first one. The second one says y goes to 1. Well, here y goes to 1 means the other term goes to 0. So x goes to 1. So it's the same thing as the following. This is the same as y going to 1. I want y, of course, of, cancel everything, 1 over 2, so it's 1 over 2. Different from 0, so limit p going to 1, 1, f of p, this minus. Clearly, this approach is not always trivially true, or easy at least, or feasible. You cannot always do such things. But because we have polynomials at the top and at the bottom, by equating their powers, we can reach a non-zero limit value. And then when we part back, we see that for that we have to choose something like this. Okay. So this shows that indeed there is no limit there.